Good afternoon, everybody. Thank you for coming back to the My Tutor online school this afternoon. Sorry we're running a few minutes late, but it's really good to see lots of you here again for another GCSE Physics session. As you can see, this one is a session on magnetic fields of electrical currents, and it will be run by Preshayla, who always does our GCSE Physics sessions, and I think lots of you know her by now, but if you don't, then this is just a recap to say that she's one of our best tutors, and she studies physics at Loughborough University, and also to say that this session will be an hour long and it will be recorded, so you'll be able to access the session afterwards as always. I'm just going to hand over to Preshayla now to lead the session for you.
Cool. Okay, so what we're going to cover today is quite content heavy and a few difficult concepts to get your head around. So we're going to be talking about the formation of a magnetic field in different scenarios, know how a compass can be used to provide evidence for the magnetic field of the Earth, know that a current carrying wire produces a magnetic field around it, learn what a solenoid is and how it forms an electromagnet, and know some applications of electromagnets and how they work. Then we'll go through some example questions and time for your questions at the end. Okay, so we're going to start off by talking about the poles of a magnet. So I'm sure you all know from Key Stage 3 Physics about the poles of a magnet. We have a north pole and we have a south pole. The North Pole is usually depicted in red and the South Pole is usually blue. So that's how you can kind of tell if the letters weren't there for any reason. Now the poles of the magnet is where the magnetic force is strongest. Okay, so if you're really close to the pole, the end of the magnet, that's going to have a bigger magnetic force than if you're further away. Okay, so we've seen that when we're playing around with magnets. If the magnet is closer to a paperclip, for example, it picks it up a lot easier than if it's further away. So that's all that means. Now, as you can see in the diagram, opposite poles attract and like poles repel. So if we have a north and a south pole like we do here, then they are going to attract each other. The same thing if it was going to be a south here and a north here, they both attract as well. However, if we have the same pole, so for example north and north and south, then they are going to repel each other. Okay, so like poles repel. Now, the magnetic force is an example of a non-contact force. Okay, so we know that, for example, a magnet and a paperclip are attracted to each other. They don't have to be touching for that magnetic force to be felt. The magnetic force can be felt by both things at a distance. Okay, so they don't need to be touching for the force to be felt. An example of a force that is a contact force, is friction. Okay, so we know that for friction to exist, two surfaces need to be rubbing against each other or gliding against each other. That's an example of a contact force. However, the magnetic force is non-contact. So really kind of brief introduction, refresh your minds. Okay, so moving on to magnetic fields. So we know that a bar magnet or any permanent magnet produces its own magnetic field. So if we have a bar magnet just sitting on the table, it has a magnetic field around it. And anything that we put into that magnetic field feels that magnetic force. Okay, so a permanent magnet produces its own field around itself. Now, an induced magnet is a material that becomes a magnet when it's placed in a magnetic field. So, for example, if we were to put that paperclip into that field, leave it there, rub it on the magnet, that would become an induced magnet. Okay, so now when we take that paperclip out of the field, it's magnetized and other things attract it. Okay, so there's two types of magnet, a permanent magnet and an induced magnet. The induced magnet is a magnetic material that only becomes a magnet if it's placed in a permanent magnetic field. Now, permanent magnets are bar magnets, the kind of horseshoe-shaped magnets. They're both examples of permanent magnets. So they're going to forever be a magnet, and that's just never going to change. And if you leave it on a table, then it creates this magnetic field around it. The magnetic field in this diagram is depicted by these magnetic field lines, which are these black lines with arrows on. So as I said, the region around a magnet where a force acts on another magnet or on a magnetic material is a magnetic field. So what that means is if we have a bar magnet and we put a paperclip into the field of the bar magnet, that paperclip is going to feel a force. Or if we were to put another magnet, so for example, another bar magnet, into the original bar magnet's field, the new bar magnet is going to feel a force. So you can either put another magnet in or a magnetic material. So for example, a paperclip, iron, steel, cobalt, or nickel. So those things, a magnet or any of those materials, when placed in an existing magnetic field, become magnetic materials. So magnetic field lines point from north to south, always. Okay, so if we have a north and a south pole, the magnetic field lines are going to be coming out of the north and going to the south, which we can see here. The arrowheads always point to the south. So you can see they're curving round, curving round, curving round. Obviously this one doesn't really look like it's pointing to the south, but it is. You have to just kind of imagine it going all the way around. Okay, so magnetic field lines, no matter what, always point from north to south. Okay, so there's a little kind of mini practical that schools kind of do. So sometimes classes do this in the classroom to kind of prove the existence of the Earth's magnetic field. And it's not a required practical, but it is a practical that you're expected to know, and questions do come up about it very often. So I'm sure you've seen a compass, you might have used it for like DOV or something. So a physical compass is a circular kind of mechanism which has an arrow in it, and it tells you north, east, south and west. Now that compass, inside it has a very, very small bar magnet. Okay, now that bar magnet, the arrow points in the direction of the Earth's magnetic field. So that bar magnet inside works with the Earth's magnetic field, and the arrow points in the direction of the north. Okay, so magnetic fields can be mapped out using these small compasses. So let's say we have a bar magnet. So we're just going to put it on a piece of paper, we're going to put our bar magnet on a piece of paper, and we're going to take our small plotting compasses. And we're going to place those compasses at lots of different points around the bar magnet. Okay, so you can see here that they've put it in this kind of C shape on both sides, and you're going to put lots of these compasses around. Now those arrows point to the magnetic south. Yeah, so they're always pointing to the magnetic south. And the direction of the arrows allows us to mark out the magnetic field lines. So you may have done a similar experiment with iron filings. So this is where you place a bar magnet underneath the paper on top, and then you sprinkle lots and lots of iron filings on top, and the iron filings make the shape of the magnetic field. Okay, same thing, but instead of iron filings, we're using compasses. And we put those compasses around the bar magnet, and the direction of the arrows shows us the direction and the shape of the magnetic field lines. So compasses are much more useful than iron filings when looking at magnetic field lines. The reason for this is because iron filings don't tell us the direction of the magnetic field lines. However, compasses do. Okay, so we've done our compasses, we've set them up nicely, and then we're going to trace the direction of each of the arrows to come up with some magnetic field lines. And it won't be perfect, but if you put a kind of point here, so where the arrow faces, point here, point here, point here, and then you join up all those points, you're going to get a pretty decent magnetic field line. So that's what that mini practical does. Now, the behaviour of a compass shows that the Earth has a magnetic field. The Earth's core is made from iron and nickel, which we know are magnetic materials. And this produces a magnetic field of the Earth. Now, we know that our Earth has a North Pole and a South Pole. Okay, North Pole and a South Pole. But actually, North Pole is magnetic south and South Pole is magnetic north. So if you think about the Earth with a big bar magnet inside of it, the South Pole points upwards and the North Pole points downwards. Okay, and this is the experiment which shows that the Earth has a magnetic field. Okay, so some rules about magnetic field lines. They must never ever cross each other. So when you're drawing them, which you most likely will have to do, you can see that they never ever cross each other. Okay. The closer the lines, the stronger the magnetic field. So as I said at the very beginning, closest to the poles, the magnetic field is the strongest. We feel the strongest force when we're close to the poles. And that is represented by the magnetic field lines. So at the poles, we see that the magnetic field lines are very close together, but away from the poles, they get further and further apart, which shows a stronger to weaker magnetic field. Now, the lines have arrowheads to show the direction of the force exerted on a magnetic North Pole. So what that means is the arrowheads always point from north to south. So they're the rules of magnetic field lines, and they must be followed when you're drawing magnetic field lines out. Okay, so one thing that I'm going to start doing in my webinars, so if you've been in our webinars before, you know we normally do quick fire questions at the end, but we're going to start doing them after each kind of subsection. So could you guys, you kind of know the drill, put your answers in the chat to these 3 questions, have a think. So the first question is, how many poles does the bar magnet have? Which combination of magnetic poles will repel each other? And which of these is a magnetic material? So I'll give you 30 seconds to have a think about those. So which combination will repel each other? Okay, so how many poles does a bar magnet have? Just two, north and south. Which combination of magnetic poles will repel each other? Well, like poles repel, so north and north. North and south will attract because opposites attract. South and north will attract because opposites attract. Third one, which of these is a magnetic material? That's iron. Okay, so next 3 questions. What happens to an induced magnet when it leaves the magnetic field? Haven't talked about this one, but let's see if you know it. What is the test for a permanent magnet, and where is a magnetic field strongest? So I'll give you a minute to do this one. Okay, 30 more seconds. Think about, for the induced magnet one, when an induced magnet is in the magnetic field, it's only magnetized because of that magnet, that original magnet. If you take it out of the magnetic field, what would happen? The only reason it's magnetized is because it's in the vicinity of the original magnet. Okay, so for the first one, the magnetism is lost. So the induced magnet is only magnetized if it's in the magnetic field. If it leaves the magnetic field, that magnetism is lost. It's no longer an induced magnet. Okay. What is the test for a permanent magnet? Okay, so what is the test for a permanent magnet? The magnet repels another magnet. Okay, so repulsion is the test for a magnet. Okay, now induced magnets will only be attracted to another magnet. They won't repel. So if a magnet can repel another magnet, it's a permanent magnet. If it can only attract, it's an induced magnet. Induced magnets can only attract. And you've never been able to repel a paperclip, have you? Because a paperclip is an induced magnet. Okay, so induced magnets will only be attracted. They will never repel. So if a magnet is repelling another magnet, you know that they're both permanent magnets. Okay, so repulsion is the test for a permanent magnet. The magnet repels another magnet, not a magnetic material, another magnet. And where is the magnetic field strongest? Where the field lines are closest together. Okay. Finally, in which direction are the arrows on a magnetic field line? Why does the Earth have a magnetic field? And what instrument can be used to map a magnetic field? Let's give you 20 seconds for these. Okay, so the first one is from north to south. Why does the Earth have a magnetic field? That's because the Earth's core is magnetic. And what instrument can be used to map a magnetic field? That's a plotting compass, like we saw in the mini practical. Okay, so moving on to the next section of our content. So this is talking about current and magnetic fields. So when a current flows through a wire, so if it's connected to a battery, a circular magnetic field is made around it. So we have a straight wire. Around that wire is circles of magnetic field. The strength of the magnetic field depends on the current in the wire. So if it's a high current, it's a higher magnetic field, stronger magnetic field, and the distance from the wire. So if we're further away from the wire, the magnetic field is weaker. There's a rule that goes along with current and magnetic fields. And the way that it works is this. You're going to do a thumbs up and you're going to point your thumb in the direction of the current. So on the left-hand side of the diagram, we see that the current is going upwards. So we point our thumb upwards. We then look to the curling of the rest of our fingers. Okay, so you can see that mine are curling this way. So that tells you which way the magnetic field lines go around the wire. So if the current goes upwards, then the magnetic field lines are anti-clockwise. Then for the other one, if the current's pointing downwards, you can see that the magnetic field lines go clockwise. You can still do it with left and you can still do it with right. Okay? So sometimes you will be asked to draw the magnetic field lines, and that's the rule that makes it really easy. Okay, so moving on to this thing called a solenoid. So as all a solenoid is a coil of wire. Okay, a coil of wire with constant kind of diameter of the coils. This is what the magnetic field lines look like. Now, outside the solenoid, the small magnetic fields from each wire cancel each other out, and their field outside the solenoid is much weaker. Inside the solenoid, however, the small magnetic fields of each coil add together and make a strong magnetic field. So we have a very strong magnetic field inside the solenoid and a very weak magnetic field outside the solenoid. And that is because the addition of the little magnetic fields of each coil or the cancelling out of each little magnetic field. Now, with this solenoid comes an equation. So with the current carrying wire and the solenoid comes an equation. So for a conductor just means a wire that carries a current at right angles to a magnetic field. So you can see that it's a right angle between the conductor and the magnetic field. Carrying a current, we have this equation. So it's quite specific. It can only be a conductor. It only works if you're at right angles to a magnetic field. And it only works if it's carrying a current. If it's just a wire with nothing attached to it, there's no magnetic field. Only when the wire has a current running through it do we have a magnetic field. So 3 conditions that need to be met to be able to use this equation. If those conditions are met, we have the equation force equals magnetic flux density times current times length, otherwise shortened to F equals BIL. F is force, B is magnetic flux density, I is current, and L is length. Magnetic flux density is a property of a material which tells us how good it is at keeping magnetism. F force is measured in newtons, B, magnetic flux density is measured in Tesla, so a new unit that we've not seen before. Length is measured in meters and I is measured in amps. So magnetic flux density is just this new kind of quantity that we use when we're talking about magnetic fields. And it's how concentrated the magnetism is in that material. You don't need to know the definition of it, so don't worry about that. It's really just a property that you'll be given. Okay, so making an electromagnet. So we're taking our solenoid one step further. So you can see our solenoid here, the orange wire, lots and lots of coils of wire. Now, when we put an iron nail in the middle of our solenoid, it becomes an electromagnet. It uses this idea of electricity and magnetism and binds them together to create an electromagnet. The reason that we put the iron core in the center is because it increases the solenoid's magnetic field strength. So we can create a really, really strong magnet which can be switched on and off. Okay, so really strong magnet, that's really great, really useful. And it can be switched on and off. Again, really, really useful, and you'll see why in a sec. So electromagnets have lots and lots of uses because they've got so many kind of functions. We can turn them on and off. They can be really strong. We can make them stronger. We can make them weaker. So really, really good applications that electromagnets have. So again, we've got our mini quiz, just 2 questions this time. What is a solenoid and how does a solenoid achieve a much greater field, magnetic field than a bar magnet? So put your answers on the chat. Let's see if you know what a solenoid is and how it achieves a better magnetic field or bigger than a bar magnet. So 5 seconds. Okay, so the solenoid is a long, thin spiral of wire used to produce a magnetic field. And how does a solenoid achieve a much greater magnetic field than a bar magnet? It adds lots of small fields together to make a larger one. Okay, so it takes the field of each of those little coils of wire and it adds them up. So you can imagine that the more coils of wire we have, the stronger the magnet, the stronger the magnetic field. So it takes each magnetic field of each coil and adds them up. And that's how we get a really big magnetic field inside the solenoid, which makes them a lot better than bar magnets. Okay, so lastly, we're just going to go over some applications of electromagnets. So the first one that we're going to look at is the Scrapyard crane. And we're going to go through 4, however, there could be different ones come up in the exam that you've not seen before. But these 4 come up often and are good to know because it is a very, very kind of tested exam question. So scrap vehicles are lifted in a scrapyard using powerful electromagnets. Now the steel frame of a vehicle sticks to the electromagnet when current passes through the coil of the electromagnet. So when we turn that electromagnet on, when we pass the current through the coil of wire, which is around the iron nail, the electromagnet kind of switches on and becomes magnetized. That then allows the vehicles to be stuck to the electromagnet and the crane can pick it up. Okay, so that all happens using a very powerful electromagnet. Then we switch the current off, the electromagnet demagnetizes and the vehicle falls off. That's how the scrapyard crane works. Moving on then to another application, which is the circuit breaker. So a circuit breaker is in series with an electromagnet. So a circuit breaker is in series with an electromagnet. The switch is held closed by a spring. When the current is too large, the switch is pulled open by the electromagnet and it stays open until it's reset. So the electromagnet attracts the switch and forces it open, which breaks the circuit. Okay, so the electromagnet can detect if that current gets too large, it will attract the spring and open the switch. If the switch is opened, the circuit is broken. Okay, another application, and this is probably the most common, is the electric bell. So here you can see you've got a battery connected to an electromagnet. So remember, electromagnet is solenoid wrapped around an iron core. That then goes to an iron armature. Now, iron armature is just a posh word for the thing that hits the bell. Make and break switch, so that's going to action the armature, and a springy metal strip. Okay, so when an electric bell is connected to a battery, the iron armature is pulled on by the electromagnet, sorry, that should say. This opens the make and break switch and the electromagnet is switched off. Okay, so if the make and break switch is open, the electromagnet has no current going through it and is not magnetized. Because of this, the armature springs back and the make and break switch closes again. So the whole cycle repeats. So it's about this magnetizing and demagnetizing using the current being turned on and off to create this ringing effect, right? It hits and goes away, hits, goes away, hits, goes away. And that's a ringing that we hear of the bell. Because of this really, really quick turning on and off of the current, and therefore the magnetization and the demagnetization of the electromagnet. Okay. Lastly, we are moving on to the relay. So the relay is used to switch an electrical machine with a high current on or off. Now, a small current here that we put through the electromagnet magnetizes the iron core and pulls on the armature again. So we put a current through the electromagnet, which turns the electromagnet on. It makes it magnetized. Then, because it's magnetized, it attracts this iron armature. Now, because it's on a pivot, if this iron armature comes down in contact with the electromagnet, this pivot hits the switch. It closes the switch gap up here, so it brings them together, and this switches the machine on. So if those two are in contact with each other, we get a full circuit and the machine is switched on. In this way, we can use a small current to switch on a machine with a much bigger current. That's cost effective. And it's all by using our electromagnet. So just to explain it again, we get a current going through the electromagnet, which goes in here. This current magnetizes the electromagnet. So it makes the electromagnet turn on, get magnetized. When that happens, it's now kind of, it's now an induced magnet, right? So it attracts the iron armature. Then the pivot allows the iron armature, when the iron armature goes down, it hits the orange things here. If it hits that, the switch gap goes together, go in contact with each other, get a complete circuit, and our machine switches on. So the machine's over here. Okay, so that's how that works. Okay, so that's the end of all of our content. I'm going to take a few questions now. Okay, this is a really interesting question. So what makes a material able to be attracted to a magnet? So this is due to intrinsic properties of a material. So you'll notice that only iron, steel, cobalt and nickel are magnetic. So they're the most common magnetic materials. And this is because of properties within the material that allow it to be magnetized. Okay, so little kind of things in the material that allow it to be magnetized. They're called dipoles, if you do want to have a look. So it's about the material itself, what's going on inside the atoms, what's going on inside the molecules that mean that it can be magnetized. Why does an iron core increase the magnetic field strength? So an iron core is magnetic, and therefore we have the coils interacting with the iron core, making stronger magnetic fields. AQA, yes, this exam board for all the webinars that I do are AQA. And I think that's all of them. Is east and west poles as well? No, there's no east and west poles for magnets, but on a compass there are. But that's got nothing to do with magnets. It's just kind of halfway between north and south. Okay, I think that's all of them for now. If there are any more that you guys have after we do these questions, do just put them on the chat and I'll get to them. Okay, so let's go through some example questions. So could you please have a go? If you've got paper with you, try and have a go at drawing the magnetic field between two north poles together, two south poles together, and two opposite poles together. Don't worry about the fact that it says seeking there. That just means north. Sometimes they write it as north seeking. It's just north. So we want you to draw. What would the magnetic field lines look like if we had a north and a north? What would the magnetic field lines look like if we had a south and a south? And a north and a south. So have a go at drawing those if you've got a piece of paper with you, and then we'll go through the answers in a second to see if you got it correct. So 1 minute, have a go. If you don't have a piece of paper, try to describe it. in your head, or you can put it in the chat if you'd like. How do you think they would look? Try and visualize the magnetic field lines. Okay. So if you got something like this, really well done. So remember, we have rules about our magnetic field lines. They can never cross, and they always point from north to south, with the arrowheads kind of depicting that direction. So for the north and south attracting, we have north to south field lines. For the north and north attracting, we have this kind of diamond shape in the middle, because the north is trying so hard to get to the south. So if we imagine that field line carried on, it's going to look like this. Okay, so if you imagine those carried on, they try to go to the south. So that's what creates this diamond shape. And the same on the bottom, try to get to the south. Then the same with south and south, except the arrowheads are going to point into the south. So remember, they go from the north into the south. Okay, so that's what the field lines look like for biomagnets attracting and repelling. Very, very, very common exam question. So it's important that you know these off by heart, or know how to derive what they would look like. Okay, so an electromagnet, as we know, is made up of a solenoid. Figure 2 shows a solenoid where the current is coming in this side and the current is going out this side. What would the magnetic field of the solenoid look like? So which way would the magnetic field lines point? What would the magnetic field line look like? Okay, so the field lines in a solenoid look a little something like this. So we're going to go through like this. And start to loop round. So we're going to go like that. So one of those things that you just have to memorize, that you just have to learn what the magnetic field lines look like. Again, a very common exam question. Remembering to put your arrowheads on, it's never enough just to draw the shape of the magnetic field lines. The whole reason that they get you to draw them is because they want to know the direction. Okay, so moving on to the next questions. This is going to be using F equals BIL. So we've got various questions here asking you to work out different parts of this equation. So for the first one, we have a cable that experiences a force of 15 newtons when placed in a magnetic field of 0.8 Teslas. That's what that T stands for. If the current in the cable is 4.8 amps, how much of the cable has been placed in the field? So this is asking us to find the length of the cable. Yeah, the length of the cable that is under this influence of field. So let's first rearrange our equation for length. So we know that we need to divide both sides by B and we need to divide both sides by I so that we can get L alone. Okay, so we have a force of 15 newtons. We have a magnetic field strength of 0.8 or magnetic flux density. And we have a current of 4.8. So work it out on your calculators. What would the length be? Put your answers in the chat. So we're doing 15 over 0.8 times 4.8. So we should be getting 3.91. So the length is 3.91 meters. Okay, so that's how much of the cable has been placed in the field. So we'll do another one like that. What is the magnetic field flux density if 2.5 meters of wire carrying 2 amps of current experiences a force of 6 newtons? Underlined all our important information. Now we're going to write out the equation that we need to use. So the equation that we need to use is F equals BIL. Then we need to rearrange our equation for what we're trying to find. So we're trying to find the magnetic flux density. So let's rearrange our equation to that. We do F divided by IL equals B. So I won't tell you what to put in your calculators. Let's see if you guys can have a go on your own. The information's all up there. You've been given force, you've been given current, and you've been given L. So let's see if you can try to find out what the magnetic flux density is and try to give the correct units. Cool, lots of you putting your answers in chat, which is really great. The answer is 1.2 Teslas. Okay, so that would be the magnetic flux density of that. Notice how we attempted that question. So we underlined all the important information. We wrote down the equation that we think we might want to use. We looked at the question and we saw what we were trying to work out. We rearranged the equation for what we're trying to work out. Then we put the numbers in and got the correct unit. One step that we didn't have to do, but is very important, is to check the units of all of the information. Now, personally, I would do that as soon as I've read the question. So read the question, underline the information, and then check the unit. So here we were fine because we had meters, which is good, amps, which is good, and newtons, which is good. However, that really easily could have been millimeters, milliamps, or kilonewtons. Okay, so do make sure you check, then you can carry on and write down the equation. Okay, so we'll go through this final question before we end. It's a scrapyard question. So in a scrapyard, we use the electromagnet to release and lift cars. Suggest 2 ways a solenoid could be made to lift and release cars in a scrapyard. So how could that solenoid be used to lift the cars? So I'll give you a few seconds to have a think about that. Put some ideas in the chat if you have any. Okay, so something that we could do with the solenoid is use add an iron core to the center of the solenoid to increase the effect of the field. So we have a solenoid, but it's not too strong. By putting an iron core in the center, we increase that magnetic field, and therefore we can turn it into an electromagnet and pick up the cars easily. So increasing the effect of the field. We could also include a switch in the circuit so that it can pick up and drop the cars. So by including a switch in our circuit, we can turn the electromagnet on and off. So we can demagnetize and magnetize the electromagnet so that it can pick up the cars, transport them, and drop the cars. Okay, so that's all of the content and the questions that we'll go through today. Yeah.
Great, thank you, Preshayla. Thank you everyone for joining us. As we said, this session has been recorded, and if you're sticking around, then we'll see you this afternoon for some of our more sessions. Thank you, bye.
Thanks, bye.